So what was V0 over IN? Speak up. Okay, so let's do it this way. So we, in the home assignment, there was a circuit, right, where I had asked you to find out the RTH, right? So what was the RTH of this? This cannot be 1 over GM. If you have RL, it cannot be 1 over GM, right? So what was it? You don't remember? Work it out. I presume you must have done the home assignment, right? Oh, yeah, so I removed it, right? Okay, so this is Vx, right? RF plus RL. RF or RL? Okay. Okay. So it is RF or RL? Oh, hold on. This thing. Yeah, fine. So makes sense because if RL goes to 0, everything you should get RF, right? Because it's basically a short circuit between Vx and Y. Okay, fine. So if you know this, then what will be this? So how do you approach this if you already know this information? So you can simply, I mean, there are multiple ways. You can do KCL, KVL, or alternatively, you can simply find out what is Vx, because Vx is IN times RTH, right? Minus IN times RF. So V0 will be IN times RTH minus IN times RF, right? So, so what happens if what was the I mean, what was the second part of it that I had asked you, that if under what condition V0 becomes minus IN times RF? Right. So there was another part, right? V0 under what condition V0 equal to minus IN times RF? Yeah, RT should be 0, but in terms of GM and all those things, all those parameters. Yeah, fine. So GMRL should be much greater than 1, but is that sufficient? And also GM, basically GM should be much greater than GF, right? I mean, GM has to be much greater than GL and GF, both. Okay. So now, okay, so this is the maths part of it, but the more important part of it is, and when this condition is met, as you pointed out, input impedance RTH essentially goes to 0. Okay, so RTH tends to 0 when these two conditions are met. So when RTH tends to 0, what type of, or if this is the input, if you consider this to be the input port, if the input port impedance goes to 0, tends to go to 0, what type of control source can you apply at the input, or what type of source can you apply at the input to get what you want, or what type of control source is this? This is essentially a control source. This entire contraption is a control source. So this behaves more like a current control source or voltage control source. Current control source, because input impedance is 0, right? Input impedance is going at, I mean, if these conditions are met, input impedance essentially goes to as low a value as you want, right? And that makes, I mean, one can always argue that if I put in a current source, the current source does, I mean, the current from the source doesn't have anywhere else to go but into the circuit, right? So what's the big deal about the input impedance? The big deal about the input impedance is the fact that no current source is ideal. So you will have some output impedance of the source. Okay, so but in the presence of output impedance, you still want most of this current I in flowing into this contraption, right? If RTH is comparable to ROS in this case, then obviously the current will not go into RTH, it will go into ROS, and you don't want that, because if you are using a current source input, then you would want most of the current to go inside the block that you are driving. Questions? Okay. So essentially, that's the main reason you would want to use anything like this under these conditions. That if you, let's say you have a block which spits out a current and you want to drive something from that block directly, right? So one way to do it is maybe convert that current into voltage and then drive another block then drive a block which can take a voltage. But another way, a simpler way, it might be, if you have a current that is coming from the preceding stage, you make the following block input stage in such a way that the input impedance goes to 0. So in that case, you don't have to put anything in between, right? It's almost like saying I have created a virtual short, right? Input impedance going to 0 effectively means that in this case, Vx is approximately going to 0, which means that your Vx, that the looking into this port, you are getting a virtual short. Okay, so anywhere you will see that I want to push in a current, right? So you would like to ensure that by design, you have to ensure that the block that you are pushing the current in behaves somewhat like a virtual short. It's not, I mean, obviously in real life, you'll not be able to get exact short, but the condition that you'll have to meet is essentially the fact that the input impedance looking into that block has to be much, much lesser than the impedance of the source that it is driving. Now, when you are designing, this source will not be a current source as is. It might be a source. It might be another block that is driving this block. And that block might be a current source. That block might be a output, might have an output stage which behaves like a current source. And it should not surprise you at this point, because a transistor essentially is a voltage controlled current source, right? So very, very often you will see that whenever you are driving something with a transistor, essentially the transistor is spitting out current. And if you have to then drive something, then it's probably easier to ensure that whatever you are driving can accept a current input. And whenever we say that some block can accept a current input, essentially what we mean is that the input impedance to that block is much lesser than whatever it's being driven with. Okay, so this is the current control source. Now, what about the output? I mean, one is current controlled source, but whatever, is it a current controlled current source or a current controlled voltage source? These are only two other options, right? How will you figure out whether it's a current controlled current source or current controlled voltage source? And what test will you put this through to come to that conclusion that whether it is a voltage source or a current source?
So load is connected across this dependent current source.
Okay.
So that means the output is voltage.
Okay, but is that always the case? I mean, I can have a current source connected to a load, and that load output can be varying with the value of the current, right? So yeah, it's okay, you have an output, you have an input, right? So you have two terminals essentially, right? You have Vx and you have V0. So if you consider this to be a box, So you can include RL inside the box, or you may not include RL inside the box. It's up to you. Even if you include RL inside the box, what do you think it will be? Because this V0 is the output terminal, right? That's a good question. You should always ask that from where am I seeing it, because the impedance or characteristics might change depending upon which terminal you are looking at. So what is the primary thing that you look for in a voltage source or a current source? Voltage should be independent of load, right? So do you think the voltage is independent of load in this case? Yeah, right. So if all these conditions is met, I am getting this. Okay, so voltage is independent of load, which means this is a voltage source. It's a current controlled voltage source. What is the other way of estimating? I mean, one way to figure out is this is obviously find out the whole input output characteristics and see whether whether the voltage at the output is independent of the load. Definitely. What is the other way of seeing? What is the other way of estimating whether it's a voltage source or a current source?
Output impedance should be as well.
Correct. So you have to figure out what is the output impedance, and as long as the output impedance is much lower than the load that you are driving, I mean that this block is driving, then you know that it's a voltage source. Alternatively, it becomes a current source. Okay. So I mean, I leave it up to you to figure out whether this is actually true or not in this particular case. Okay. Any questions regarding this? So this was the last control source that was remaining. So I mean, I didn't synthesize it in this case, but you can also, I mean, go about and figure out how to synthesize it from the scratch. Again, you start off with what is desired, what is actual, and try to minimize the difference between desired and actual by manufacturing a difference. You can do it yourself. If you are not comfortable, let me know next class. I will briefly touch upon it also. Okay. So in the last class, we were essentially looking into manufacturing a voltage controlled voltage source with a proportionally constant more than 1. And we said that we'll do it with a integrator in the loop, because the integrator also helps us in visualizing the dynamics with which the final output settling happens, right? So we came up heuristically with this block diagram. And then we argued that if Vi is a step input, or rather if Vi is essentially DC, if you are looking at it for long time, then V0 can be nothing but K times Vi, because if it's anything other than K times Vi, the input of the integrator will have a non-zero DC voltage. And as long as the input of an integrator has a non-zero DC voltage, it will keep on driving in the direction to reduce the error, right? And as long as your loop is in negative feedback, the error will go to 0 only when the integrator, only when you wait for infinite time, which in other parlance means that since the integrator has has infinite loop gain at 0 frequency, the integrator will only get satisfied when the input to its input is essentially 0. Other way of saying it is that you will essentially achieve a virtual short between the error terminals, right? What is the error terminal? You have, these are the error terminals. And I mean, when you have some element which has infinite loop gain in the loop, you will end up achieving a virtual short as long as you have made sure that the entire thing is in negative feedback and the loop has infinite loop gain. Okay, so and then we were moving into what happens if we have a non-zero frequency, because I mean, obviously you are not really always bothered about processing DC signals or processing step signals. You might also want to process sinusoidal or time varying signals, which essentially means that we need to understand the characteristics of this loop when we apply sinusoids, because essentially sinusoids are building blocks for all signals that we play with. Okay.
So if the loop gain is infinite, in that case, 0 input will lead to finite output, but 0 error voltage will lead to finite output.
Right. Yeah. right? So yeah, exactly, right? So that's the main conclusion out of it, that you can have zero input and finite output, but what the finite output what will the final output doesn't depend on the integrator. It depends on whatever you have wrapped around it. Okay, so you can have, so this input will be zero regardless of Vi is a 1 volt step or 2 volt step or 5 volt step, doesn't matter. Okay, if you wait infinite time, V will go to zero, but V naught will be K times 1 volt or K times 2 volt or K times 5 volts, will depend upon whatever is wrapped around that integrator. The purpose of the integrator is only to ensure that its input goes to zero, is only to ensure that your virtual ground is satisfied. So that is a good way to, when you will be designing circuits, there will be projects where you'll be designing circuits. You will probably see that under certain circumstances, you have designed your circuit for maybe gain of 5 or 6 or 2 or whatever, and you will see that you are probably not able to meet that gain. Maybe it's slightly higher, maybe it's slightly lower. Then how do you go about debugging it? What is the first step you might want to do? Often, if you are doing it for the first time, one temptation is to go and fix the integrator, simply because you are driving something, right? So, if I just draw a block diagram like this, and you know that something is driving this, and you have an output here, and if something goes wrong with the output, then the natural thing to assess is that maybe whatever is driving the block has gone wrong. Okay, and that's how we are trained to think, right? So whatever is driving the output has gone wrong. But when things are in negative feedback, you have to think from the back, think from the opposite side. And what is it? Essentially, you see that whatever it is driving is a forward path, and your feedback loop is more or less insensitive to forward path. That's the whole idea of making a negative feedback loop. Okay, so the whole purpose of this integrator is to give you large gain. If the gain goes from maybe 1 million to 1.5 million, you will really not see too much of a difference at the output voltage. Okay, so even though one might argue that, hey, everything is a negative feedback, so everything affects everything, but you have to identify which thing in your negative feedback loop affects the output more than the other. And obviously, in this case, the sensor, that is in this case, the resistor divider, will play more significant role in affecting the output than the input. Okay, the chances of things going wrong in the feedback in the sensor path and affecting your output disproportionately is much higher than chances of things going wrong in the forward path. Okay, so that is one thing that you have to see. So whenever you are analyzing negative feedback loop, you have to take, it's always difficult to analyze in the forward direction. You have to go the other way around. So that's a general tip that I give to everybody. So you might want to pay heed to that as well. Okay, so let's delve into this circuit, this block diagram a bit more. So let's assume that you have the same circuit, but let's say I have inserted a error voltage. I have inserted a step input. It's a 1 volt step, and let's assume the input is grounded. Okay. So can you comment on what will V naught look like eventually as a function of time, or on also eventually what will it look like? So what I'm saying is you have, let me mark it. Let's say I have inserted Vn, and Vn is, let's say, a step. So what will V naught look like qualitatively? I just want to see whether you have understood the crux of this negative feedback. There can be different answers, like, so let's have some answers, right? So I heard something from this side. What was it? It will be ramp. It will be ramp from the time you have the step. Then it will go ramp, and it will ramp It will keep on ramping. Okay, so this is one possible scenario that it keeps on ramping. Any other scenarios? And when will it? So it will ramp and then stop after some time. And when will it stop? Error is 0. Okay, fine. So when error is 0, what happens? Error means you mean this error, I presume, right? So when this error becomes 0, then what can you conclude? So this is what I mean by working backwards. So only thing that is sacrosanct in the loop is if you have infinite gain, error will go to 0. If the error goes to 0, what can you comment on this voltage? 0, right? So if this is 0, what is V naught? V naught will be 1. Why? Correct. So so we'll do the step thing also, but let's assume that we have waited infinite time and the loop has settled.
So I think the slope will be the slope of the ramp will be negative, right? So this 1 volt voltage is getting divided through this resistor divider, and then there is a negative side.
Okay.
The error voltage will be initially negative.
Okay.
And so I think it will be the slope of the shape will be negative.
And what will happen after infinite time? It's easier to figure out what will happen at DC, right? Then we can work the dynamics. So somebody said 0, somebody said it will be 1, right? So at infinite time, there was saying that it will either be 0 of t equal to infinity, or it will probably be 1. So, I mean, obviously something has to give, right? You cannot have discontinuity. You will have, if you have a ramp, it has to come down to 1, or it has to come down to 0, or whether it will be a ramp in the first place. There are a lot of questions which needs to be answered. So let's do the steady state first, then we'll answer this.
So start from this 1 volt.
Okay, we'll do the starting later. So I mean, I want to see if the class is convinced with what the final output will be after waiting for infinite time. It will be 0. Okay, how many of you think it's 0? Okay, how many of you think it's 1? And how many of you think it will keep on ramping? Okay, again, you have a lot of no thinkers. Okay. So, but I want to hear from no thinkers actually. I mean, what are you thinking? Obviously, you're thinking, I mean, something. Maybe you are confused or something has, I mean, you were munching something in your mind, but not coming to a conclusion. That is also fine, but I want to hear your thought process. What is causing the issue? What is it that that is not giving you a conclusion? What is confusing you? You have to speak out, otherwise I cannot really, I mean, navigate. I want feedback from you, right? Otherwise I'll go in open loop in some other direction. You'll not understand what's going on, because this is still in block diagram. If you don't understand this, you'll not understand when I put circuits in. So extremely crucial that you understand this. So speak up. So I'll not talk till I hear something. So I'll pause the recording. No, if V0 is a step, what will be this voltage? It's a voltage divider, right? While, I mean, then how is it 0? I mean, this voltage is K, V0 by K, isn't it? So this is V0 by K, isn't it? This is a resistor divider. Right? So will it be now 0 or V0 by K or whatever, 1 volt by K?
So virtual grounding is failing. So is that a condition? We are adding something, taking out the current, then virtual ground fails.
No, will the virtual round fail? Why do you see, why are you coming to the conclusion that the virtual round should fail?
This situation at t equals to 0, right?
No, not equal to the infinite time, steady state. Things have settled. Okay, tell me whether it's a negative feedback or positive feedback. Negative feedback, right? So negative feedback, infinite gain op amp in the loop, virtual round should hold or not hold? It should hold, right? So now if virtual round holds, now what do you think V0 will be? It has to be 0, right? So same thing here, right? So same thing here at the, when after you wait till t equal to infinity, what is sacrosanct again in negative feedback loop? Input of the integrator has to go to 0 if at DC, right? That is crucial because at DC only DC you have infinite gain. So the input of the integrator has to go to 0 at DC, which means that you will have, if this is 0 volt, means this has to be at 0 volt. If this is 0 volt, this is 0 volt, which means output has nowhere else to go but to go to 0. So this is another way of, showing you how you don't approach the problem through the forward path, right? It's basically the feedback, the wrapper around the high gain path that determines what the final output will be. Now you have to see how it settles to 0, how it goes to 0, because we had several answers, right? One answer was it was ramping up. Now if it's ramping up in this direction, then if it has to go to 0, it has to change slope somewhere, right? It has to go somewhere like this and then go.
Sir, one point.
Yes.
I told that it is the ramp function.
Huh.
So it cannot be ramp function, sir, because the error voltage is changing.
Yeah.
With time.
Correct.
It is a constant. In that case, it will be ramp.
Yeah. Yeah. So that's a good starting point. That can it be a ramp function all the time in a negative feedback loop? When can it be a ramp? If the output can only be a ramp if you have a constant input at the input of the integrator. The integrator is the only driving block here, right? Everything else is sensing. So if integrator is the only driving block, then only when you have a constant input at the input of the integrator, that output will be a ramp. Okay. So the whole purpose of putting a negative feedback is to ensure that the input of the integrator doesn't go to some finite DC value, right? So which means the loop will keep on correcting all the time. How it will correct, that we'll see. Okay, but it will keep on correcting. So two conclusions. One is output at steady state will go to 0. Second conclusion is that it cannot be a ramp all the time. Okay, the third has to be the third thing that we need to figure out at time t equal to 0, what's going to happen. Or when I'm not t equal to 0 in this case, at time t equal to t0, let's say, what's going to happen. Okay, so let's do that intuitively first. So at time t equal to t0, when you are pushing this step, okay, so let's go the other way around and let's go from infinity towards backwards, right? So we understood that at time t equal to infinity, the output will go to 0. Okay. So if at time t equal to infinity, output goes to 0, comment on this voltage. I want to see if the rest of the class agrees or disagrees. The output of the integrator, just at the output of the integrator, what will it be? It has to be -1 because otherwise output cannot be 0, right? So this has to go to -1. So if I plot this one, this will name it, right? So let's say, what should I name it? It's a Vx. So Vx will be at -1. Now, in order to figure out how the final output will settle, I need to figure out essentially how will Vx settle. right? Because I know what Vn is. Vn is a step. So if I can figure out how Vx will settle, I should be able to figure out how the final output will settle. Now, what do you think? How will Vx? What will be the starting point of Vx at time t equal to t naught? I know that it will end up at -1, but at time t equal to t naught, what will be Vx? When I'm just hit it with the ramp.
It will be 0.
Why it will be 0?
Because of the initial capacitor integrator do not have any charge.
Okay.
It will start charging, but at t equals to t naught, the error voltage is basically 1 by k.
Okay.
So it will start to integrate, but initially it is 0. But there is the slope.
Okay, we'll come to the slope. So his point is that Vx at time t equal to t naught will be 0. Do you agree?
Yes, sir.
Okay. So yeah. So why do you agree? Yeah. So another way of saying the same thing is that, as you pointed out, that integrator, I mean, the integrator can give a sudden jump at the output only when you have infinite input, right? Only if you have impulse kind of input, that then and only then your integrator can give a finite output. In other words, when you're integrating, if you have something finite and you are trying to integrate it from time t equal to 0, obviously integrator has to start from 0, right? Because it's a summer, it's a running summer. You are starting from 0, which means it has to be 0. So Vx will start from 0. So Vx will start from 0. So now I know that Vx will start from 0 and it will go to -1. Now the question is, how will it go to -1? Can you comment? I mean, without doing the maths. I mean, I will leave the maths to you. That will be maybe a part of the home assignment. But can you comment on how will it go to -1 from 0 to -1? Okay, it's a exponential, and what will be the? I mean, we characterize exponential with the time constant, right? If you know the initial and you know the final, all you need to know is the time constant. So what will be the time constant? So it will go something like this. Right? So what will be the time constant of this exponential? Yeah, right. It should be k by w, because ultimately time constant is a property of the system. Okay, so and in the last class we saw what is the time constant if I apply an input at, let's say, the traditional input point, right? So output was settling exponentially at, I mean, k times Vp times 1 minus e power t by tau, where tau was k by omega u. Okay, so since if you have figured out the time constant of a circuit once, you don't have to do it multiple times. Whatever you do, time constant doesn't really change. So this settling, this tau will be k by omega u. Okay, so now if this settling characteristic looks like this, what do you think? Now comment on how will the final V naught look like? Yeah, right. So V naught is essentially Vn plus this. Okay, so it will start from 1 volt and then it will go to 0. And this time constant again will be the same as this tau. Okay, and this should make sense to you because I mean, the final thing definitely should make sense to you, because the whole purpose of putting a negative feedback is to stabilize any excursions or any non-idealities in your circuit, right? So that's the whole reason we have put negative feedback. Now, we initially said that we want this output to be independent of ambient change. You might consider this to be some sort of ambient change, right? Maybe it's some noise or something that I have pushed in somewhere in the loop, and that has caused this. That has caused some deviation at the output, but you cannot expect any loop to correct any excursions immediately. So it will take some time, but eventually it will correct. So this what eventually means in this case, it means infinite time. At infinite time, output will go to whatever it was supposed to be. And what in the absence of an input, your output was supposed to be 0. It will go to 0, but it will not go to 0 immediately. It will go to 0 after some time, and that time is essentially the property of the loop, and that is the time constant, that is k by omega u. And again, if you want your circuit to be, your loop to be very, very responsive to any excursions, or in other words, you want to ensure that the loop suppresses any excursions, you have to ensure that your this factor of omega u over k has to be as high as possible. Okay. Any questions? So let me ask you another question then. Let's say I have applied a 1 volt excursion here, and this is grounded. What will be V naught? Steady state, let's say. Let's say this is 1 volt. This is Vn. Okay, so what will be V naught? Let's do it again the way we did, right? So at steady state, what will be V naught?
It will be a ramp signal.
It will be a ramp signal. Why?
Because here this integrator will integrate the small signal, whatever input we are applying here, because this is feedback to
Okay.
go back and get integrated.
Okay, so now let's do that intuitively, right? So the output starts integrating, right? So this output starts ramping up. If this ramps up, this ramps up, or ramping up or ramping down. Firstly, that you have to tell me. It will ramp down, right? So this is positive, so this is positive, this is negative. So this will ramp down. So when it ramps down, what happens to the error? Error will decrease, right? So the error voltage will decrease, isn't it?
Steady state, we have to be minus
Right. So again, I mean, go the backward route, right? So at steady state, what is sacrosanct?
error voltage is zero.
Error voltage at the input of the error amplifier is 0. Okay. So what is, which means what? Which means this is 0. This has to be 0. If this is 0, what has to be this one? This has to be -1. If this is -1, what has to be V0? Minus k, right? So V0 has to be minus k. So this is, so at infinite, it would settle when V0 equal to minus k. Okay.
So, this error voltage is zero. This is only applicable when this negative feedback system.
In infinite gain.
In infinite
Under infinite gain.
and
Yeah.
negative feedback.
Yeah.
And sir, in that case, we also have to look for the output and input while identifying the negative feedback or positive feedback.
No, right? I mean, you don't have to look at the output of the input. How do you identify whether things is negative feedback or not? You essentially break the loop hypothetically, apply some input. I mean, apply some test voltage and see test voltage or current, or see whatever comes back, the return one is in the opposite direction to the excursions or the same direction. If it reinforces, it's positive feedback. If it goes the other way around, it's negative feedback. Right? So, so how many of you have, I mean, obviously there was some of you agreed to the fact that the output will go to will be RAM, but clearly looks like it's not the scenario, right? Output finally will go to minus K. So why do you think this answer makes sense? And why is it that when I applied an excursion in this situation, output ultimately settled to 0, and when I applied an excursion in this situation, the output essentially went bonkers, right? It went to minus K.
So actually, in the first case, that voltage divider is basically dividing the voltage, and it is in the error voltage.
Okay.
But here, this particular voltage directly coming to the error voltage. Okay, so the error voltage. So you mentioned it is the feedback loop.
Yeah, same thing, right? Exactly this circuit.
Yeah. First you mentioned
Can you repeat? Maybe, I mean, I couldn't get what you said. Okay. 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 Yeah. So essentially what she's saying is, I mean, adding an input here is equivalent to adding an input here, right? Right? I can push the summer. Adding an input there is equivalent to adding an input here, but with a negative sign, because there is a, so it's equivalent to saying that I have applied an input of -1 volt at the traditional place. So the output has to be minus K, right? So that's true, but I mean, the answer that I'm actually looking for is the fact that, see, you have changed something in the sensing path, right? I mean, go back to the scenario of driving. If your speedometer is broken, you will take a wrong decision. Okay. Or even, I mean, another maybe more relatable analogy. In fact, it has happened to me also multiple times. Maybe if you have your earphones on and you have forgot to plug in the earphone jack, right? And you think that nothing is coming out, so you keep on increasing the volume, right? So it's something similar to that. So you have error in the sensing path. So whenever you have error in the sensing path, obviously your decision making will be wrong, and which essentially in this case means that you have gone to a different direction. Okay, so again, so output will go to minus K, and where will it start from? Where will it start from? At t equal to t0, it will start from 0, and it will eventually settle to minus K with the same time constant. Okay. Okay. Yes.
as long as loop gain is very high,
Yeah.
we are very much sure that output will settle.
If okay, in this first order system, there is no instability, yes, output will settle.
So it will be 0 or minus K, something depending on the where I'm applying the input.
In this particular case, but it might not be minus K also. I can give a slightly different circuit, some different way of sensing. In that case, it might not be minus K.
So the forward path will define the output.
Forward path never defines the output, right? Why do you say forward path is defining the output?
The first circuit and second circuit.
Yeah.
Loop gain is same.
Correct.
But what we are doing, we are replacing the input in different places.
Correct.
So forward path gain is changing.
Forward path gain is not changing, right? I mean, when you say, so help me understand this. So when you say forward path gain, what do you mean? Do you mean omega u over s?
No, sir. Input and output ratio of output.
Okay, you mean the transfer function between wherever you are applying to? Yeah, clearly that has changed, right? So that's the more mathematical way of going about doing your things, right? So what I want all of you to do is to, as if thank you for pointing that out. So what I want you to do is to figure out the transfer function between these points, right? Figure out the transfer function when you apply an input here to here, or when I apply an input to the final output, right? So find out V0 over Vi when Vi is different located at different points of the loop. Okay, and then see, then you can say that, see what the dynamics will be if that Vi is a step. Okay, so the thing that we did in the last class was we applied Vi here, and we saw how the final output will settle. We did it mathematically. So what I want you to do yourself is to not only apply it there, apply at the two other places that we talked about here, and then see how the final output will settle. Okay, that's a good exercise, and you should do it. Okay. Okay, fine. So now let's look into a slightly more realistic scenario. And the realistic scenario is, let's assume your integrator is not ideal. Okay, so you have integrator which is omega u by s plus p. Yeah, 1 second. Yes.
So the take-home message from the last discussion is basically whenever the noise is present in the follower path, that gets suppressed, but if it is present in the sensing path, that may cause.
That will cause a problem, right? So it's always the same scenario in any feedback loop. Whatever is driving the final output, a feedback loop is largely insensitive to changes in that path, right? As long as the driving strength is large enough. Like in this case, is infinite, which means that any change in the forward path will not affect, as long as your gain is high. But all these analogies that I have done till now is at DC. You have to be mindful of that, right? So things will change slightly when you apply a time varying input, and that will make sense because when you have a sinusoidal input, integrator no longer has infinite gain. Integrator has an infinite gain only at DC. So your ideal op-amp kind of scenario is no longer valid if you have a non-DC input. Okay. So before going into that non-DC input, let me walk you through what's going to happen if let's say the integrator is not ideal. Okay. So which essentially means that integrator has a finite DC gain. So one way of modeling that is I say that integrator transfer function is omega u by s plus p, which means I can say this is omega u by p by 1 plus s by p. So this omega u by p is the DC gain, and this is the pole. Okay. So other way of, now if I plot this with respect to so with respect to omega, initially what would I have got? I would have gotten, if we had assumed that, let's assume p was 0. Okay, the ideal integrator, the p was 0, I would have probably gotten something like this, where this point would have been so it's in this particular case it's omega u, but if I plot the loop gain, right? So this is only the integrator, right? So if I plot the loop gain on top of this, so this is omega u over s. So if I plot loop gain, let's say L of s, what is the expression for L of s in this particular circuit?
Minus omega u by k divided by s plus p.
Well, not minus, right? Yeah. So again, how do you figure out loop gain? You desensitize the input, break the loop, apply a test voltage, right? So because many of you seem to be a bit dated, so let me do this once again. You apply V test. The output is V test omega u by s plus p, and this becomes V test omega u by s plus p k, and minus of that appears here. That is the return voltage, which means L of s is minus V test by V return, which is in this case omega u by k s plus p. So I will always try to keep this omega u by k term jumbled together because it keeps on appearing everywhere. Okay. So so now if I plot L of s, mod of L of j omega, rather, not L of s. So what should I see? In an ideal case where p is 0, this is when p equal to 0. So when p equal to 0, what should L of s be? With respect to the first plot, it will be on top of it, moving to the right or moving to the left.
Yes, omega
K is more than 1. It should go to the left, right? So the entire thing will go shift to the left. So this is a different color. So this is omega u over ks. Okay. So now this is the scenario with ideal integrator that we had been dealing with till now. But now I am saying I have a real integrator, but you don't have infinite DC gain, you have some finite DC gain, and which I have expressed is in this form, right? In this form. Let me call it L non-ideal or L real. Okay. So if I plot this L real of S or j omega, comment on how will this look like? Okay, so other thing that I forgot to mark is what will be that 0 dB crossing point in this case, omega u by k. Good. So now let's do this real integrator stuff. At DC, it will be flat, and you'll have a gain, and the gain is omega u over k by k times p, right? So you just put s equal to 0, you'll get flat. So this will be a DC, or let me just say L of 0. Okay. So now what will happen after that? Where? It will encounter a pole, that's right. And where will that? At P. And can you comment on whether whether the P will be somewhere here, somewhere here? I mean, is there a way to figure it out? So if you use Bode approximations, right? If you use what is Bode approximation? Is the fact that you can use straight line segments to define your gain transfer functions before and after a pole. Okay, so let's assume that we have crossed the pole P. Wherever the pole P might be, we have crossed the pole P. So what will the transfer function look like when I have crossed the pole P? So mod of L of j omega, or rather simply L of, let's say, L r of s for omega greater than P. How can I approximate it using Bode approximations? No, I want the transfer function. I mean, I have the transfer function here. I want to use Bode approximation, and I will approximate it using Bode approximation. So what will this transfer function look like? Right, so P will simply be gone because I have crossed P, right? That's what Bode approximation is, right? So it's omega u by k times s. Okay, so if at omega much greater than P, if your transfer function looks like as if it was an ideal integrator. Okay, makes sense? So which essentially means that your transfer function will around wherever the pole P might be, it will, I'm assuming the pole P is before omega u over k. In that case, it will go flush on top of ideal integrator plot. Make sense? So which essentially means that you have two straight line segments and they can meet only directly on top. And this will be P. Okay. So what I want you to do again is plot this loop gain yourself. Do it yourself. Plot this loop gain yourself without making these approximations. Use Bode without going by the logic. Don't go by the logic that I just went through. Use brute force method and use Bode approximations. Okay, and then plot this loop gain and verify whether what I have said here, whether indeed the intersection points of these two will be P or not. Okay. Okay, so now, so this essentially points, I mean, it tells us a couple of things. One is that if we are operating at frequencies above P, I can assume my system to be an ideal integrator. Right? I don't have to bother about P if I am operating at frequencies above P. Right? However, if system starts to deviate at frequencies below P. Okay. So, but fortunately at frequencies below P, it doesn't look like I have any frequency dependence, at least by Bode approximation, it's flat. So I can get rid of all S and all those things terms. I can simply assume my integrator to be an ideal gain block and go about doing my analysis. Make sense? So if we do that, what will we get? So now at omega less than P, right? At omega less than P, what will my integrator look like? Let me write out the full transfer function, then we can do the approximation. Okay, so now let's put a step at Vi as we initially had put. This is 1 volt step. So not forget about the dynamics. Now tell me what will the output settle to after time t equal to infinity, final settling. Will it settle to k times Vi?
Yes.
Why? So let me ask you, so is Vi, V0 is k times Vi or anything else?
So in this case, the error voltage is not 0, right? Whatever this pole is present
Yeah, what do you mean by error voltage is not 0?
at DC in steady state.
Yeah, so in this case, the integrator doesn't have infinite gain at DC, right? So if I have to analyze what's going on at DC, I can simply say that I'm not looking at the dynamics of how the final settling will be. I'm only interested in the steady state. So in that case, I can simply replace this integrator block by putting S equal to 0, and which means this is simply a gain block of ADC is equal to omega U by Kp, right? So now if you have a negative feedback loop with this gain, what will be final output be? No, K, it will not be K into Vi, right? It will be K into Vi only when you have infinite gain. Now you don't have infinite gain.
Yes, okay.
Isn't it? So see, in the earlier case, the integrator was not able to sustain a non-DC input because the integrator would have kept on driving. But now look, just look into this Bode plot, and if let's say you have a non-DC input, the integrator doesn't have infinite gain, right? Sorry, I made the choice of word was not correct. So let me rephrase. What I'm saying is that if you have an ideal integrator and if you have a DC input, it cannot sustain a finite input error voltage. Because if you have a finite input error voltage, integrator has infinite gain, it will keep ramping. But now the integrator doesn't have infinite gain. So which essentially means that there is a solution where the integrator can sustain a finite input voltage. Okay. So if the integrator can sustain a finite input voltage, which essentially means that your virtual ground no longer holds true, right? But depending upon how large the gain is, it will be closer and closer to virtual ground. But if you have a finite input voltage, a finite gain in the loop, a finite gain in the integrator, your virtual ground no longer strictly holds true, which means there will be some error voltage here, some error voltage here. And that error voltage, we call it a steady state error. Okay. So if I use the block diagrammatic representation let's assume I call it L of S. Something like this. And the gain at DC is L of 0. So what will be the steady state error? Or let me ask you, what will be V naught in terms of VI in this block diagram? V naught by VI will be? Pardon? L by 1 by L, right? LS by 1 by L. And when you are talking about DC input, your V0 over Vi is L of 0 by 1 plus L of 0. Okay. So which means at steady state, what is the error? Ideally, L of 0 has to be, what is the ideal thing that you are shooting for? Infinite, right? So ideally, L of S is an integrator. So L of 0 has to be infinite. In this, if it's infinite, then L by 1 plus L is 1. Right? But in reality, if L of 0 is finite, so you will get some steady state error. Will be 1 minus V0 by Vi. Why 1? Because 1 is the scenario I would have got in an ideal case, right? So this becomes, so this has to be multiplied by Vi, right? Because error is something either voltage or current. So this is 1 by 1 plus L of 0 times Vi. Okay, so as you see that if L of 0 goes to infinity, then the steady state error goes to 0, and that's what we have been arguing for so long, that if the integrator is ideal, your output has to be 0. Okay, but in this case, if the integrator is not ideal, that is, it has a finite DC gain, you will have some error, and this error is approximately equal to Vi by L of 0. As long as L of 0 is much greater than 1, your steady state error is approximately equal to Vi by L of 0. So this is true for L of 0, much greater than 1. So this is another approximation that you have to be aware of, right? So if I ask you what is the steady state error, then you cannot say that infinite has I mean, if it's a non-ideal integrator, you cannot make the assumption that it's infinite and steady state error is 0, right? Because when I'm asking for steady state error, I'm asking for this small value. But when I'm asking you what is the final output, you may say that, okay, fine, final output is K times Vi or whatever the actual it's supposed to be, because then you are neglecting the steady state error with respect to a larger final output, right? So again, the same thing, you cannot neglect anything with respect to 0, but you can neglect a small thing with respect to a large thing. So again, make that approximate, you feel free to make that approximation, right? Okay, so we are out of time almost. Any questions before we wrap up?
In this case, non-ideal case, the error voltage is non-zero, and we have some finite output. So I was thinking like that integrator is taking some error voltage, but the output is stable. So can I think like this way, that as the integrator is non-ideal, maybe there is some resistive part. So the capacitor is basically discharging, but to mitigate that, some error voltage is continuously rising.
Yeah, so we haven't put actually capacitors and resistors till now. We'll get into that. We'll get to that. You can think of it in this way, that there is an integrator action. There is an integrator action between P and omega U, but below P there is no more integrator. Below frequency P there is no more integrator. It's flat.
So what type of, like,
it's a constant gain block then. It's a constant gain block, right? So that's all it's happening. So constant gain essentially means there is no frequency dependent elements. Okay, so we'll get to those things. So before we break, so before the next class, what I want you to do is make a note of the things that I have asked you to do yourself. So find out the transfer function from various parts of the loop to V0. Then figure out using Bode approximation whether indeed this magenta line will cut the green line exactly at where I have shown here. And the third one, what I want you to do is, okay, so third one that I want you to do, I also follow up in the next class, is the fact that find out the final settling of the loop when your integrator has finite DC gain, right? So mathematical expression when you have this scenario. So find V naught t when VIT is a step. For this case, you know that we did it for the ideal integrator case, but I want you to do in the real integrator case. And I'll assume that all of you will do it, and I'll just take the final output, ask somebody, and then start it for next class. Okay. Okay.